This is an extension, I guess, of what we looked at with quadratics. Playing around with the relationship between the roots and the coefficients. Now, you remember, I hope, in the quadratic, so the general one, ax squared plus bx plus c is 0, and we saw that the sum of the roots was minus b on a, and the product of the roots was c on a. Now, that idea extends through all polynomials. So if we have a cubic, and if we generalise it, but we stay consistent and we make a always the leading coefficient, and then just go down the alphabet, b, c, d, the sum of the roots will still be minus b on a. But now there's an extra root. So alpha plus beta plus gamma. The product of the roots, well, we don't now call this the product of the roots. What we say is it's the sum of the roots 2 at a time. So when we take all the possible pairings. So we now have this additional one, alpha, beta, gamma, 3 at a time. And that becomes minus d on a. So the signs alternate. It starts minus, then plus, then minus, and so on. So if we had a quartic, sum of the roots, 1 at a time, is minus b on a. Sum of the roots, 2 at a time, c on a. Sum of the roots, 3 at a time, minus d on a. And 4 at a time, e on a. Question. How did I know when I looked at the sum of the roots 2 at a time that there was going to be 6 of them?
Combination.
Yeah. So it's 4c2 because you're saying there's 4 roots and I'm just choosing 2 at a time. So 4c2. To generalise, so I could have any polynomial as long as I make a the leading coefficient. Those who like shorthand, Owen, you'll love this. Instead of writing alpha plus beta plus gamma plus delta plus however many roots, we can just write sigma alpha. Because capital sigma, of course, is the arithmetic sum. And that's minus b on a. So that will always be. Notice, sum of the roots, 1 at a time. Alpha beta will always be c on a. So sum of all the roots, 2 at a time. 3 at a time, minus d on a. 4 at a time, e on a. I could keep going. Interestingly, this idea that we saw in the quadratic, when we had that common question, alpha squared plus beta squared, that also transferred to all polynomials. So if you have the sum of the roots 1 at a time squared, so alpha squared plus beta squared plus gamma squared and so on, it will always be the sum of the roots 1 at a time, all squared, minus 2 times the sum of the roots 2 at a time. So that idea always carries through. Let's play with this one. By the way, you don't really see much more than a quartic. And most of the time we just have cubics, but the idea, as I say, does flow through to other ones. We got a cubic. We're going to find, because it's interesting, 4 alpha plus 4 beta plus 4 gamma minus 7 alpha beta gamma. Oh well, let's find the sum of the roots 1 at a time, 5 on 2. May as well do 2 at a time, because there's probably going to be other parts and we're going to need it. So we'll find the basics. If they're nice in the question, they would actually make that part I, so at least you got a gift mark. You can, get some marks for that. In this case, it's a simple one, isn't it? We just substitute in. So I've got 4 lots of 1 at a time minus 7 lots of 3 at a time. And we get 27 on 2. The reciprocal, algebraic fraction. So the denominator ends up being 3 at a time. The numerator, 2 at a time. So we'll have minus 3 on 2 on minus a half, which is, of course, positive 3. It's not there. Trust me, it's not there. Ooh.
What's up there?
Exactly. Sum of the roots 1 at a time squared. So I was just saying, 1 at a time all squared minus 2 times 2 at a time. In this case, 37 on 4. So all those fun manipulations we did in quadratics now become even more fun. Yes, fun is the correct word. HSC question. Here they were nice. You'll notice their first question was very much a gift. Find alpha plus beta plus gamma. Mind you, it wasn't that nice because you know what a lot of people did.
Didn't stop 3.
Yes, but it's not 3.
It's 0.
It's 0. There is no x squared term there. So it's actually 0. Then in the second part they asked for 3 at a time, and 3 at a time in this one is -1. The third one they asked for was the fraction question, the sum of the reciprocals. So just like we saw before. So subbing 2 at a time, which amazingly once again is -3 over -1, which we know the answer to be 3. 2003. Two of the roots are reciprocals of each other. We have to find the value of k. So I'm not going to say the roots are alpha, beta, gamma. I'm going to say they're alpha, 1 on alpha, and beta. Now that makes the product of the roots very easy, because the reciprocals are going to be 1. So I can certainly find one of the roots straight away. Question's not asking for that though, it is asking for k. Let's put it together. Well, if I find that root as -3, so polynomial -3 is equal to 0. This is a different way of doing it. So rather than going, I mean, the thought I guess would have been, hey, let's go 2 at a time, and then we can link k in and solve that. This idea is saying, well, hang on, if beta is -3, I know -3 is a solution. Therefore, by the factor theorem, polynomial -3 is equal to 0, and I can just sub straight in to the equation and then find out what k is. So subbing that in, eventually, we'll get there. There it is. K is 13. So I could have mucked around and tried and find alpha, and then once I had alpha, I could have then worked out k. But that's probably a bit quicker than doing that. 2006 paper. So we've got a monic, x cubed plus rx squared plus sx plus t. And it's got 3 real zeros, 1 alpha and -alpha. We have to find the value of r, the pirate letter. Okay, well again, it's going to drop out quite nicely, this one. So I just do some of the roots 1 at a time. The alpha and the -alpha are going to cancel. And that is the connection to r, is 1 at a time. And so we get straight away, r is -1. Part 2, find the value then of not s and t, but s plus t. So they're not interested in individually what s and t are, but rather the sum of them. Okay, well I know 2 at a time is s. So s I know is -alpha squared, whatever alpha happens to be. If I use 3 at a time, I get that alpha squared is t. Hang on. S is -alpha squared, t is alpha squared, s plus t is 0.